For the longest time, the name of the game in AI was just more. More data, more parameters, more compute power. Just throw more at the problem. But we're hitting this really fascinating turning point. The whole strategy is shifting away from that brute force approach to something way more sophisticated, something you could call strategic cognition. We're not just trying to get these models to think harder, we're trying to get them to think smarter. So let's dive in and figure out what that actually looks like.
Okay, so check this out. This quote from a really recent paper, well, it should make any AI architect just stop and stare. For a while now, the go-to wisdom, especially with those agentic frameworks like React, where you tell the model to think, then act, was to make it plan out its next move every single time. But what this new research is showing is the complete opposite. It turns out forcing an AI to constantly be in planning mode can actually make it perform worse and even fail at what it's trying to do. And that right there is the big puzzle we're going to unpack. It just doesn't seem to make sense, right? How can making an AI think more, spending more compute on planning, which sounds like a good thing, actually lead to a worse result? The answer is, well, it's pretty wild, and it points to a huge shift in how we have to think about building the next wave of AI agents. All right, so to really get our heads around this paradox, we have to change the way we think about AI compute. It's not just this infinite well of power you can keep drawing from. A much better way to look at it now is like a budget, a strategic budget that you have to spend wisely, with some real intelligence and precision. And the core idea here has a name. It's called test time compute. And just to be super clear, this has zero to do with training the model. This is all about what happens when it's actually running at inference time. It's about giving the model the ability to say, whoa, this problem is tough. I'm going to need to think a little harder. And then on the flip side, just cruise through the easy stuff. Suddenly, compute isn't this fixed cost anymore. It's a dynamic resource the model can manage itself. Now, this whole idea of a compute budget, it's part of a much bigger shift that's happening. Honestly, we're moving past the era of prompt engineering. The new game is context engineering. We're not just tweaking the input prompt anymore, we're managing the model's entire world. Its memory, the tools it has access to, and yeah, that limited budget for thinking, all while it's working on some long, complicated task. This isn't just about writing better prompts. It's about designing a whole system. So, okay, how does this smart, budget-minded approach to compute actually work when it comes to AI agents that need to plan things out? Well, this is where we get to what I like to call the Goldilocks paradox. And it's seriously fascinating, because it turns out too much planning isn't just a waste of time and money, it can actually be bad for the model's performance. Let's break it down. On one side, you've got the old method, the kind of naive React style. Here, the agent is basically stuck in a loop, forced to plan before every single action. It burns through tokens like crazy. And as we're learning, it just doesn't work well. But on the other side, you have this Goldilocks method, dynamic planning. This is where the agent has picked up a new, higher-level skill. It knows when it needs to stop and think, and it spends that precious compute budget only when it's absolutely necessary. And hey, this isn't just some abstract idea. We've got the data to back it up. This chart right here shows the Goldilocks effect in action, clear as day. Look over on the left, never plan. Obviously, performance is low. But then look at always plan. It's also bad. It's actually way worse than the peak. And where's that peak, that sweet spot? It's right in the middle, when the agent plans only once every 4 steps or so. It's just proof. There's an optimal amount of thinking. Okay, so why? Why does thinking too much break things? Researchers have a term for it: instability cost. Basically, when a model replans all the time, tiny little errors or noise in its own thinking get amplified. It starts second-guessing itself, constantly changing its mind, and getting stuck, bouncing back and forth between 2 steps. It'll even abandon a great plan for no good reason. It is, and I mean this literally, overthinking itself into complete failure. Okay, so if we know that this dynamic, Goldilocks planning, is the way to go, how do we actually build an AI that can do it? What's the secret sauce in the architecture? Well, that brings us to the mechanics of something called interleaved thinking. It's all about how these new models can pause, think, and act, all in one smooth, continuous loop. So this is the interleaved reasoning loop, and it's a really big deal. The old way was for the model to think once, then spit out a bunch of actions. But look at this cycle. The model thinks, then it does something, like calls a tool, it gets a result back from that tool, and here's the magic part. It thinks again to make sense of that new info before it does anything else. And this whole thing, think, act, get result, think again, it all happens seamlessly in what looks like a single turn to the user. And listen, this isn't some far-off futuristic concept. This is real right now. This quote from the Claude API docs proves it. You can go use this today. Models like Claude 3.5 Sonnet, they already do this interleaved thinking automatically whenever they use tools. So for all you developers out there, this is huge. It means you can build agents that are way, way smarter, chaining together different tools and actually thinking about the results at each step. Now, all this amazing new reasoning power, it creates a new and equally huge problem: security. I mean, think about it. If the model is writing down its entire thought process step by step, you've just opened up a massive new way for things to go wrong. And here's the really critical part. That same chain of thought, the very thing that makes the models so smart, can also expose, well, everything. We're talking about your secret system prompts, your company's proprietary logic, maybe even API keys you've got hard-coded in there. It's all just sitting in that reasoning trace. This is such a big deal that OWASP has actually added it to their top 10 list of vulnerabilities for LLMs. It's a serious, serious risk. So what's the fix? Well, it's an architectural solution that people are calling private thinking or summarized thinking. The idea is simple but brilliant. The model does all that powerful step-by-step reasoning on the inside, but that raw, messy thought process never actually gets sent out through the API. So you, the user, get the final intelligent answer, but without the massive security hole of seeing how the sausage was made. So if you're building these systems, the advantages here are just massive. This immediately slams the door on system prompt leakage. It helps shut down those nasty indirect prompt injection attacks. It shields your company's secret sauce, your business logic. And it can even stop reward hacking because attackers can't see the full thought process to game the system. It's a huge security win. All right, let's tie all of this together. What does this actually mean for us, the people who are building with this tech every day? It means we need a whole new playbook, a new set of rules for designing AI agents that are not just powerful, but also strategic, efficient, and, most importantly, secure. So here they are, the new design principles for this era. It's a real shift in focus, isn't it? We're moving away from just chasing raw power and towards strategic efficiency. We're talking about tuning for that Goldilocks planning frequency. We're architecting for those interleaved reasoning loops. We're treating compute like the finite budget it is. And crucially, we're thinking about security from the ground up by walling off that internal thinking process. We're graduating from prompt engineering to full-on context engineering. And all of this really leaves us with one big final question to chew on. As these AI models get better and better at managing their own thinking, at deciding for themselves when to think hard and when to coast, what does our job as engineers even look like? We're not really puppet masters pulling every string anymore, are we? We're becoming more like architects, designing the environments for these autonomous cognitive systems to operate in. So the question we have to ask ourselves isn't just how do we make it more powerful, it's how do we teach it the wisdom to use that power well?